I'll cover the third problem next, since the second problem is the hardest one in the set. Okay, so in the in the third problem, what you have is you can do two types of operation. We have operation of type one, where you pick a number L, and what you do is you have actually I should start off by defining some terms. So you start off with an array of length n, and your goal is to eventually turn all the elements in the array to zero. And to turn them all into zero, you have two types of operation. So in your first type of operation, you pick an integer L, and what you do is you have um it's let me yeah, okay. So you have a of n minus L increases by zero, and then a of n minus L plus one increases by one, and so on and so forth until you have a of n increases by L. And your second type of operation, which is type two, is the same thing, but instead of increasing, you're decreasing. So here you have a of n minus L minus equals zero, and a of n minus L plus one minus is equal to one, and so on and so forth. And the question is, what is the minimum number of operations in total of both types combined you need to apply to eventually turn all the array elements into zero? So so to solve this problem, you need to observe a couple of things. So I'm gonna erase this. To Jaden, this is the second problem, or this is the third problem. Yeah. So the first thing you notice that is it's never optimal to do an operation of type one for a certain L and then do it for type two for a certain L, because the two operations would cancel out and you would have done two operations for nothing, and would have been more optimal to just not have done anything at all. So that's the first important observation. And the second important observation is that no, we're currently on problem three. The second important observation is that if you consider the first element in the array, I don't know what happened just now. If you consider a of one, you can only ever use operations with L is equal to n minus one to update array of one, because all the other operations stop too short. For instance, let me again. If you set L to be equal to you set yeah. Oh no, actually sorry. If you set L to be I got one of the definitions mixed up earlier. If you set L to be oh sure. I should I should send the statements. Give me a second. Um Let me see if this works. Oh, okay. Cool. Okay. I sent three images in the Zoom chat, each corresponding to the problem statement of that particular problem. And then we're currently on problem three. Oh, what I said earlier was wrong. I got L and I got the definition of an operation confused. It's that you have like sorry. If you have an operation of type so like an operation of type L um has an array of n minus L plus one. No, actually no, I didn't get it wrong. Yeah, plus equals to one, and then array of n minus L plus two plus equals to two, and so on. So anyway, so well, what you can notice is that first off, the only type of operation that can affect array of one is the type of operation when L is equal to n. This is true because if you set L to be anything lower than n, say you picked n minus three or something, you you actually you actually won't change array of one because you'll only ever change the furthest left, the smallest element, the smallest index you will change is equal to n minus L plus one. And you have to set L to be L equals to n in order to edit the first number in the array. So what this means is that the number of operations of type L equals to n is actually, or like you know that will, so say array of one is greater than zero. In the event that it's great, or I should say less than zero, that'd make more sense. In the event that array of one is less than zero, we need exactly array of one operations of type two, or type one. Yeah, operations of type one to make array of one equal to zero. Because in each operation, we are setting, well, in each operation, we're going to increase the value of array of one by one. So after applying exactly a of one operations, you would have set a of one equals to zero. And then in the second case where a of one is greater than zero, then you also need exactly a of one operations of type two. And it's the same logic. And in particular, you can't do it in less than a of one operations because if you use less than a of one operations, you wouldn't have actually changed the value at all. And you also don't need more than a of one operations because earlier we demonstrated that there's no need to use more than one operation, more than one different. There's no need to use a type one or a type two operation at the same time for fixed L because they cancel each other. So we know that we need to use exactly a of one operations of type L. So say so now that we know that, um, let's say we applied all these operations to the array. So after we applied all these operations to the array, we now have a of one is equal to zero. And actually, we can solve the exact same problem again for a of two, because the same logic still applies. You only operations of type L is equal to m minus one can change array of two. And basically, this logic, by using this logic, you can set the numbers from one all the way to n in increasing order. You set them to zero one at a time, and each time you know exactly what type of operation you want to use. So the only tricky part now is how we can effectively simulate how we can effectively simulate applying all the operations. Because after trying each L, we can't actually update the array directly. That would result in an n squared algorithm, which would TLE. So, so what is needed is that we have to. So what is needed is that we have to simulate this in a smart manner, and the way you can simulate it well is that say we know that we used say that we know that we used here. Okay, if we used, sorry, my pen is having issues right now. So if we used X operations of type one, use X operations of type one, And then we used y of type 2. And then in addition to that, we also store the sum of all the operations that we've like done so far, which would be how do I put this? Yeah. So okay, if we store the total sum of the effects of all the operations we've done so far, let's keep that in a value called sum. So basically, every single time we apply an operation of type 1, sum will increase. And every single time we apply an operation of type 2, sum will decrease. And the important thing is that when you consider the effect of all the if you consider the effect of all the operations on array of I, and you think about the effects of operations of array of I plus 1, they're actually really similar, right? Because all the operations would have added some value x to I, and then they would have added some other value x plus 1 or subtracted x plus 1 from I plus 1. So when you move from I to I plus 1, if you know the amount of operations of type 1 you've done, you actually just have to increase sum by x, because that corresponds to taking every single operation of type 1 you've done so far and shifting all of their values of x to be x plus 1. And the same logic is true for y, which is that if you take all of the operations of type 2 you've done, it's the same as when you move from I to I plus 1, it's the same as if you just subtracted y, since you would have taken all the negative x's and changed them into negative x minus 1, or here negative x plus 1. And this is the same thing as, because you used y updates of type 2, you would have changed each one of them by -1, which is subtracting it by y. So by using this clever trick, you can actually simulate the effects of all the operations you've done so far and effectively compute how they change as you shift from one element to another. And the final thing is that in the problem, at the very end of the statement, they say it is guaranteed that the answer is at most 10 to the ninth. This doesn't seem like a very useful fact, but actually, by guaranteeing this fact, your code won't overflow a long as you run this process, because otherwise you would end up with really large numbers. But luckily for us, they guarantee that that won't happen. So that's the full solution for problem 3. I think it would probably be good if I sent code for that. So I think after I finish presenting all the solutions, I'll send like a link containing the solution codes for all of them. Okay, and then finally, I'm gonna go over problem 2, which is, I think, without a doubt, the hardest problem in the set.